Okay, so good morning, everyone. Today we'll be talking about our project, which is the analysis on bicycle rolling resistance.
I'm Kevin. Harry.
Next up. So what is rolling resistance? So simply it's the forces that work against your forward motion. So that could be, the rider's weight or the road surface that you're traveling on. So the more forces you have working against you, the more resistance you'll have, which will require you to need more power to move. And the two resistances or two losses we'll be focusing on is the hysteretic losses and the suspension losses. Hysteretic meaning that when the tire rolls, it compresses faster than it decompresses. So it's not perfectly elastic, so that creates losses there. And for the suspension losses, when you're riding a bike, vibrations are induced by the road surface that are absorbed by the rider's body. And so we want to measure, or we want to see what that data looks like and where the energy is lost. Next slide. So in our research, we found this setup where there's a drum sort of design and the tire sits on. So initially we had that one at first is that the surface is like concave and not as flat as like a regular road surface. So we wanted to implement that in our design. So we found this MTS system where the car tires are like tested and measured for durability using the system. So using this design, we're using this finding, it causes break car design. Next slide. So the two approaches or the two avenues of our project is to build a test bench or to measure hysteretic losses, and the second is to have to measure or to have a test bike to measure suspension losses. So the parameters that we'll be testing is the tire width, pressure, thickness, and speed, more in a controlled environment. And for the on-bike, the parameters that we'll be looking at is the terrain, the tire pressure, and the tire speed. Next slide. And now we'll talk more about the testing.
Okay, so as Karen mentioned earlier, the historical testing for tires has been typically on a drum, and the problem with that is it for one, it doesn't mimic real life testing. We don't ride on curved surfaces, and the drum actually exaggerates the hysteretic losses within the tire by biting deeper into the tire. So for our design, it was important for us to create a stable, flat platform for the wheel to sit on, which is what you see here in the middle. We have our wheel block in blue. And there's a polyethylene sheet underneath of it that is a low friction sheet that allows the belt to slide with as little friction as possible. And then we load it at the end of the wheel mount with a load that simulates the rider's weight. The system is driven by a motor, a shaft coupling, 2 pulleys, and a belt. And so here's some components of our design. As I mentioned earlier, it's we use a 4.25 horsepower motor. I'm sure a lot of you are like, why such large horsepower? Cost is an issue for this project, and it happened to be the cheapest motor we could find on eBay at the time to suit all our needs, so we took that one. So you got a Lovejoy coupling right there in the drivetrain that extends out to 2 pulley wheels and a belt. We have an MC60 motor controller controlled by a potentiometer to adjust the speed. The picture on the right here is our belt tensioning system that's going to help with alignment and tensioning. Okay, so for our power, the way we're going to categorize the hysteretic losses is through a power measurement. And basically compare that, compare one tire to another. The delta in power would tell us which one's more efficient. And the way we're doing that is similar to the previous presentation, is we mount our motor free to spin on the rear mount. And the only thing constraining the motor from spinning is the load cell right here. the pink item on the picture on the left. And so it's basically a Newton's third law principle where we're capturing the torque at the shaft is getting transferred back through the motor housing into the load cell. That's where we get our force times the distance of the lever arm, and then the Hall effect sensor is going to capture our RPMs, and we combine that for our power reading. So for our testing procedure, to start off, we basically ensure that the system is aligned, the pulley wheels are aligned, and then we apply attention to the belt. We load the wheel. So the wheel mount actually rotates down, so we load the wheel onto the wheel block, and then we apply the weight. The data acquisition is started, and then the system is started gradually. And so some of the issues we've been having with our system is belt tracking. It tracks significantly from time to time. And last Saturday we happened to run into a window where it was running pretty well, and we actually got this video. So during the testing, it's critical to make sure that the belt is aligned, the wheels operating properly or secured to the wheel block, and look for any issues with the system as it's moving. So we gradually run the system up to our steady state desired RPMs, and we hold it there for about a minute, and then we end our testing. And this is some of the preliminary data we got. We actually literally just finished the assembly last Saturday, and this is some of the data that we were able to get. The blue plot right there indicates the loading the load on the system without the wheel, and then the red plot indicates the loading with the 28-pound load on the wheel at 8 miles per hour. So it's what we expected. So the load cell is operating properly, and obviously we're going to need further testing to bring our data together and get more reliable plots.
Okay, so next we'll talk about our on-bike setup, which we use for measuring suspension losses. So this is the design. We have our bike here, and we're using 2 accelerometers. I'll talk about later. Only one is working right now, but the intention is to have one on the front of the bike and one on the rear of the bike, which are the top 2 red circles that I have there. And then we also have a Hall effect sensor that's at the bottom of the back wheel, and that's measuring the speed that we're going. And then each accelerometer is logging at 500 hertz, which was quite a challenge to get working because Arduinos can only sample so fast, and writing efficient code that also because Arduinos have such a small storage space, if you sample really quickly, you quickly run out of space, or you can't sample fast enough. So that was a real challenge to make it work. It's where you can sample at such a quick rate because we're trying to measure vibrations, and a quick spike in vibration, you have to sample really quickly in order to detect it. And then all the data is being saved to SD cards through the Arduino. So in testing, we select a tire to test. For now, we're using the stock tires on the bike, and then we set a tire pressure. We start with 50 psi. We record 3 runs to then be able to average later. And we ride the bike a certain distance, trying to maintain the same speed, about 7 miles per hour. And then once we're done, we stop the sensor data logging and wait for it to convert and save to the SD card. And our intention is to then run several different pressures and see what the difference in the vibrations look like with different pressures and different kinds of tires. This is an example data point. This is our first run we did at 50 psi at 7 miles per hour. This is the acceleration data. So what we're looking at is just acceleration in G's versus time. You can see it's flat at the beginning where the bike isn't moving yet. Then the bike is moving for about 24 seconds. And then it's got more data on the end where it stopped moving and it's just saving. From here, what we'll want to do is take more data measurements average them and see if we can then try a different PSI, multiple data measurements, average them, and see if we can find a statistically significant difference between the vibrational frequencies. And how we look at that is we'll do a power spectral density analysis. This is for the first data run at 50 PSI. And we can see the different frequencies of vibrations and how often they're occurring through this PSD diagram. And then we'll be able to compare different tires and different PSIs. So for the remainder of our semester, what we're going to do is try to collect more data so we can find our results. We have to try to troubleshoot the belt tracking for the test bench to make it run straight a little more frequently so we get some reliable data. And then currently the second accelerometer we haven't made working on the bike. We want to see if we can get that working, so we'll have 2 acceleration data points for every test run. And in the future, what we'd like to be able to do for like a next group would be to use a different pulley design. So upgrade the pulleys to be crowned so that the belt can track a little easier. And also potentially upgrade the belt to be rubber or a different material. And also refine the data acquisition system. So now I just want to acknowledge and thank our project advisor, Dr. Tsuchiya, and our industry sponsor, Jan Heine, with Renee Hurst, and Pedro Bustamante, who helped us machine the pulleys out of aluminum for our design. And I'd like to thank our team. There's 10 of us, and we've been putting in lots of work over these last couple semesters, and it's been a blast. Thank you. Are there any questions? I Googled it last night at 2 a.m. Then
I was supposed to send you some, right?
yeah,
Yes,
and it was. We did our testing yesterday at 4 p.m. and we finished the data. So then last night, after I had some work, I just sat down and started Googling. Okay, how do I import data from a text file into MATLAB? Then I decided I didn't want to do it that way. I put all the data in Excel, because the accelerometer actually saves to an Excel file. So I then took our RPM data, put into the same Excel. I then converted the raw acceleration data to G's, and then I went in MATLAB. I figured out how to import Excel data to MATLAB, and then I Googled how to do a PSG analysis at 2 a.m. and did that. And so basically just doing a fast Fourier transform to get the PSD.
I think my actual question is, what was your, do you happen to know what the NFT window was?
The window?
The window, yeah. This is like all like a very dense, like often you look at PSDs and it almost looks like a line, like a Bodhi magnitude plot. Sometimes it looks like this if your NFT window is really high. This looks like extraordinary. It looks like a fuzzy white line.
I think the reason it's doing that is because it's got so many data points.
It's not. Remember this frequency, right? So it's not temporal. But it has to do with that window. But you can see it's actually interesting. There's like 2 modes, right? There's one at like, I don't know, 60 hertz and one at maybe 10. That seem prominent, but I think if we mess with that window, it'll accentuate what its actual modes are.
Yeah, maybe next week I'll get with you and we'll
Take it down
figure it out. All right, any other questions? I think we're
All right, and yeah.